Hello, everyone, and welcome back to the next session of ROS Industrial Conference 2020 Virtual Edition. This session is titled Real-Time and Micro ROS, and we have 60 minutes for presentations, followed by 15 minutes for panel discussion. Today, we will have two presentations with three presenters. At the end of which we will have the panel discussion where we take up questions which you could post on Swapcard. So I encourage all viewers to take part in the polls that are already presented. You can record your responses and you can also post some questions in Swapcard. I do want to make all the viewers aware that there is about 15 seconds lag between the live event and the stream. So there could be a short delay before your questions are answered. So I would like to first introduce our first speaker, Dr. Ralph Lange. He's joining us from Renningen in Germany, which is actually not very far from here. He completed his PhD in computer science from the University of Stuttgart and has been for 8 years with Bosch Corporate Research, where he works now as a project manager in robotics systems and software engineering. He leads a project on methods, tools, and frameworks for systems and software engineering in robotics. And he is also the principal investigator in the OFERA project for Micro ROS, which aims at putting ROS-II on microcontrollers. His team supports Bosch not only in the usage of ROS, but also contributes to the development of ROS. So Dr. Ralph Lange, thank you very much for joining us. The microphone is now yours.
Thank you very much for the kind introduction, Tejas. Guess this should be minimized. Move it on there. Yeah, if you work with ROS, you're all aware of how a main function in C++ looks like, and that there is this one important call, ROS spin, which makes your main thread to serve as the spin thread of the node. Technically, there is the ROS client library, which implements basic API functions for the user code, core functionalities of ROS, which implements middleware functionality based on TCP and UDP. And once the node starts up, all incoming events from the network, messages that arrive, service calls, etc., as well as timer events are stored in a queue, the callback queue. And the task of the spin thread is to take one by one in FIFO order these events and the content from the callback queue and call the corresponding callbacks to process them. If you want to learn more about that and all the details, what happens in case of buffer overruns and so on, I recommend the presentation by my colleague Ingo Lütgebole from 2017, which still can be found on Vimeo. Now in ROS-II, things on the first glance look very similar. There's a call RCL-CPP spin, which takes a shared pointer to a node and again makes the main thread to serve as the spin thread. But we'll see in a minute that things are very different in ROS-II. And the first change that you perhaps know is that ROS-II also allows to implement nodes as components, which means you're not shipping an executable to your customer or to your users, but that you ship a shared library, which then allows to instantiate the nodes directly, for example, on the command line or using launch files. And in both cases, what happens in the background is that a so-called executor is instantiated. In the simplest case, it's called the single-threaded executor from the ROS client library. The current node is added, and then again, the spin function is invoked, which makes the main thread to serve as the spin thread for this executor. The concept of the executor makes execution management much more explicit, gives more, let's say, flexibility and allows to extend it and adapt it for your needs. In this presentation, you will learn the objectives behind the executor design. I'll introduce it to the default scheduling semantics and issues with it, and then to recent developments around this concept, the static executor, the callback group level executor. And based on, let's say, these works, we want to dig a bit deeper than in the topic of how to achieve determinism, and in particularly simple FIFO ordering, as we saw before, is common and known from ROS-I. And finally, I would present our works on the RCLC executor, which is the executor intended for micros, which then makes a smooth transition to the presentation by Francesco and Pablo on Micro ROS afterwards. This is how the stack of ROS-II looks like. There are two important differences. The first one is that ROS-II doesn't come with its own middleware, but relies on other standards, in particular DDS standards and implementations like Fast DDS, Cyclone, or RTI Connex. And for that, a middleware layer has been introduced, which makes basically three assumptions: that you have some naming concept, that you support publish subscribe in the underlying middleware, and request response. And the second important change is that the ROS client support library has been introduced, which implements all the core functionalities in C, so that the higher layers ideally have to include these functions only by their native interfaces. However, execution management is located in the high-level language APIs of the higher layers. On the first glance, this looks very similar to what we saw in ROS-I before. There's this executor instance on the high-level language client library. There are the callbacks at the top and the incoming messages, service calls, or whatever. However, the important difference is that the messages are actually queued in the middleware and not on the client library level. Therefore, the executor has to take them, and in case that it's not fast enough, the queues may also increase here on the middleware level, and especially with DDS, queues are maintained individually for each topic. So that's why the executor first has to get information about which messages are there, and that's what's called the wait action. So the executor asks the middleware to provide information on which topic is a message available. That's just a binary information, so true or false, in the sense here on the first topic goal is a message, on the last one, but not on the middle one. And then it may decide to take one of these messages and call the corresponding callback. There are two objectives behind this design. First one, it should be avoided to introduce an additional queue on the client library, to have queues on the middleware level and on the client library level. And secondly, this design utilizes the DDS quality of service mechanisms. DDS was chosen explicitly because it comes with such mechanisms to configure lifespans, histories, priorities, etc. But by this design, the decision on the distribution order and the processing order is distributed to the middleware and the client library, and that's important to keep in the back of your head. Now let's look a bit deeper in how this wait and take works. On the right-hand side, I sketched the workflow. So we start here in the beginning with nothing, they'll fall through, and then comes a function that is called collect entities. And collect entities goes through the whole structure of your node and searches for all timers, subscriptions, service, client calls, etc., and creates a vector of these middleware subscriptions. So with pointers to the subscription for, in our case, the goal, the command, and the odometry topic. Then it passes down this list to the middleware and does this wait call there, and the middleware zeroes out every pointer where no information is available, and that's then passed back, and that's what is then treated as a binary or Boolean information. There is a message or not. And once this vector is back to the executor, it works as follows. It always checks first, is there a timer ready? And that's a call not to the middleware, of course, but to the RCL, to this ROS client support library. If not, it searches for the first message that is available from this vector on a topic, takes it out, processes it, and clears the corresponding entry in the wait set. Next time it searches again for a timer. If not, searches again for topic. If all topics have been processed, it searches for service messages, for service replies to clients. And once the whole vector here has been processed, it collects entities again and waits in the middleware. Of course, this happens only if the callback execution is not fast enough, in the sense that here we are in congestion phase and messages are buffered in the middleware. If the callbacks are processed very quickly, that's in the normal case just one single message that is reported in this wait set. Real-time experts will describe this scheme as non-preemptive and a mix of priority and round robin. Why non-preemptive? Because our callbacks are executed until they are completed, so they run to completion. Priorities because timers overrule everything, and round robin because from the remaining topics, service, etc., exactly one message is processed on each topic, service, and so on, because we only have this Boolean information available, and then we ask the middleware again. So in case of congestion, that's everything, but not FIFO processing. If you want to get into the details, I recommend this paper by our PhD student Tobias Blass, which was published last year on the ECRTS conference. Now we think, what are the requirements in robotics? We have the request for end-to-end latency guarantees. If somebody traps in front of the LiDAR, we want to know the time until it takes that the motor receives the stop command. We want to have support for mixed real-time criticality. We have functions which are real-time critical, certain control loops, and other ones which are not. We need to parallelize algorithms, and we want determinism to be able to at least reproduce results and compute computations and simulations, etc., or for debugging purposes in subsystems of our system. And there are a couple of ongoing works in the ROS2 community the ROS community work on ROS2 to achieve these requirements. The one is to reduce runtime overhead introduced by this layer design and by the distribution of execution management to middleware and client library, especially on these rather costly weight set operations. We look into how to map execution management and the threads in the client library here optimally to the operating system scheduling mechanisms, and to achieve determinism, at least an important aspect of determinism, FIFO ordering, for example, by the message timestamps or by the arrival times, is another topic that is currently considered. And let's dig into these latest developments. So the multi-threaded executor is provided out of the box with the single-threaded executor. It allows to process multiple entries from this weight set in parallel. And you can configure which one can be processed in parallel and which not by the callback groups. So you can assign your callbacks to different groups. And there are two types of groups, re-entrant group and a mutually exclusive group. And the callbacks of a re-entrant group may be processed in parallel. Callbacks of different groups may be processed in parallel, but the callbacks of a multi-exclusive group must not be processed in parallel, which then saves you from thinking about synchronization mechanisms within your node when accessing shared variables between these callbacks. That's how these callback groups are created. Your node comes with a function create callback group that's provided by the parent class node in the RCL CPP. You specify this type on an enum, and then when creating a subscription, you have the possibility to pass an option object where you can specify this callback group. In case of the timer, it's even easier. That's just a third argument here at the end. If you omit this argument, a null is reported, and then a default callback group, which is always created for your node, is used. The first addition from the last year that I want to present to you is the static single-threaded executor, which has been developed by Nubleo, which I gave a talk already yesterday. And that's the static single-threaded executor. And the main difference is that this collect entities function is not called every time before waiting in the middleware, but only at the initialization, so the first time when you add your node to the executor. This had the big advantage that the searching for all the timers and elements in your node is not repeated over and over again when the structure of the node has not changed at all. You have to know that, on the other hand, if you create subscriptions timers on the fly during the execution later, they will not be considered. So for example, if this process ODAM callback and the corresponding subscription is created, if a certain message here on the command topic arrives, so inside the callback next command, then it will not be considered by this executor instance, because it was not known at the time when the node was added to the static single-threaded executor. The next work I would like to present to you is the callback group level executor. And the first important message, it's not an executor, although we used this name a lot in the last years. What it is a refinement of the existing executor API. So far, the executor allows to add a whole node, and with this refinement, you can now create multiple executor instances in your process, assign it to different threads, and map the callback groups to the different executors. This prototype was mainly developed by myself and presented at ROSCON 2018. And thanks to Pedro Pena and Intranet Open Robotics and William Woodall, this is now mainline. They brought it in September into mainline, and you can test it out already in rolling. And they not only implemented this for the default executor as in my demo there, but for all executors, so also the mentioned static single-threaded scheduling executor. So what can you do with this? For example, you have two nodes. Let's call it ping node and pong node. The ping node sends here on two messages on two paths out a ping periodically, and the pong node receives it, does some heavy computations on receiving of these messages and returns a pong. And on the pong side here, the corresponding callbacks are distributed to two callback groups and again to two executor instances. And the high path here is configured with a high prioritized thread, while the executor on the low path is prioritized very low, using the normal scheduling mechanisms of Linux, no preempt RT, nothing. And in this demo, you can configure here the CPU cycles that are used to process these. I plan to contribute them back to the standard demos. You can find the ongoing work here under this link. And then you can do experiments like increasing here the rate. So I have here configured that the high ping requires 10 milliseconds of processing, while a low ping even 40 milliseconds. So that's perhaps a more computation extensive algorithm, but less important. And with a rate of 10 Hertz, that's 500 milliseconds per second, that's happily served by the CPU. Even 20 Hertz is possible. And from there on, you see that the high BC loop is still served by the low goes down. That's the received or the actual rate that is achieved. And of course, from 100 Hertz on, the CPU is fully saturated by these 100 messages, which each needs 10 milliseconds of processing. So no chance to go further. These are, let's say, a number of stepstones, but no solution for determinism or at least FIFO ordering. And that's why we revisited this design beginning of this year and discussed how can this be improved. Again, remember, the decision on the processing orders distributed here to executor and the middleware. And you can think of two extremes. First, you could say that you decide completely in the middleware. That would even be possible with the current implementation. If you make the decision where and report in the wait set just one message, the executor cannot do anything else than just process this single message. However, on the middleware level, we lack of any application knowledge that we have, which is all the structure of the nodes, the callback groups, and so on. The other extreme is that you use a separate thread to get all the information from the middleware, which of course enforces the middleware QoS. You would take the messages from the middleware, even though they might, for example, would be expired in a few milliseconds according to core settings. And there is an intermediate approach. You could try to give a more comprehensive view on the middleware, not just a bit vector, but details on timestamp, sizes of queues, and so on. But of course, this is then more information to transport between the layers and very expensive. And there are many other subtle technical issues. What about memory management, how to integrate timers, and especially the metadata on the messages, such as the send timestamp, is not directly available in many DDS implementations, but only after you really take the message and deserialized it. That's why my colleagues Inge Lütgebohl and Carsten Knese have introduced as a first step a take with info message, which is a function which is available since Foxy now. And this not only takes the message, but also the relevant meta info from the middleware. So at least you have now the possibility on the upper layer to get all the meta information. When was the message actually sent? When was it received by the middleware? To decide on processing orders if you want. And since September, the middleware and the real-time working groups discussed a very interesting proposal by a robot, which is called the Events Executor, which gets closer to the design that you know from ROS-I. It takes the messages from the middleware as discussed before with all the downsides, but improves performance a lot by the possibility to use here DDS listen ROS, so that you don't have to pass down and work this wait set, but you're automatically notified if messages are arrived. You have the possibility to order them at least by the receiving time. And if you really take out the messages, if you create a so-called work queue here, that you really take out the messages, you have all the metadata also to sort them by the send time or receive time to come here to a deterministic and FIFO order. That's still in discussion. If you want to join the discussion, join the middleware or real-time working group meetings. Let's go over to Micro ROS, and we want to briefly present you our RCIC executor, which is implemented in C, can be also used with standard ROS too, but is mainly intended for microcontrollers. And for that, we looked into the typical patterns that we see in robotics, and especially in deeply embedded applications of microcontrollers. We have control loops, sense, plan, act cycles, where you have a clearly staged processing. We have data fusion, where we have inputs with different rates, have to synchronize, and then call computation typically driven by the lower rate. And was also very common that we have some prioritization. So here after the sense, we have two paths, but there's one that we want to process first to raise an emergency stop if necessary. And we looked into the concept from the executor and thought, how should they be extended to meet these requirements from these use patterns and use cases. The first one, we refined the API to register each callback individually. That sounds a bit complex. However, in deeply embedded software development, that's not uncommon that you think for each function or computable in which task to place it, in which order, and so on. So for the developers, that's quite common. By this individual registration, you can now precisely define a processing sequence. In this case, there's multiple events happen simultaneously. So you can say, for example, on go is always processed before next command. And the most important change is that we introduce so-called trigger conditions. So once the wait set returns from the middleware, we do not start directly processing, but we allow the developer to specify certain events to react. And so, for example, we do not process the messages before both goal and command received one message. And you can even here define trigger conditions by reacting to hardware events. That's also called guard condition concept. Can link them to timer events and so on. So interrupt, so that gives a much more flexibility to be invoked and then think about, okay, which information is where and how to process it, or should I, for example, do some alternative computation in case that no message arrived. And finally, we implemented the so-called LET semantics. LET stands for logical execution time, which is a concept developed at Berkeley 20 years ago for embedded systems. The idea is that you read in one step, then do the processing, as this processing is not interlinked via messages. The order is not relevant, so it's, let's say, very determinate or provides determinism guarantees. And at the end, you do a write. The write is still missing, but this synchronous read is what we do. That's an optional feature that you can activate in the executor. If you want to learn more about all these concepts and look into examples, check out the RCIC package in the ROS-II organization on GitHub. This concludes my presentation. I want you to know that the execution management semantics in ROS-II are very different from the one that you know from ROS-I. There is no FIFO ordering in case of congestions. The decision on the processing order is currently distributed to middleware and client library. And the key questions on improving this is how to achieve determinism, how to integrate and consider the middleware core settings that you can specify. That's an ongoing discussion. As said, join middleware real-time working group if you want to participate in this discussion. And nevertheless, a couple of new concepts have been implemented by various companies and players in the ROS community and are available in Foxy and Rolling. Check them out if you have applications where you have real-time needs or determinism requirements. Looking forward to your questions, but I guess after the Micro ROS presentation by Francesca and Pablo.
Thank you very much for your presentation, Ralph. We actually have one question from Guys, which is completely relevant to the presentation that you just gave. So maybe we can take it up right now. So he asks, in your opinion, is one of the major contributors to the complexity in executor design the desire to maintain DDS quality of service for messages at least?
Yes, that let's say causes a lot of complexity. One extreme is forget about these QoS settings, take out all messages and come up with your own, let's say, QoS scheme on the client library level. Already in ROS2, we have, let's say, somehow abstracted from the very detailed QoS settings in DDS by some pre-configured settings like this systems QoS default, sensor QoS default, and so on. You find a couple of types in the RCL CPP library for that. Of course, taking out all the messages, deserializing just to throw them away is very costly. So on the other hand, doing this in the middleware is computationally more efficient. So yeah. That's hard to decide which is the right approach. Of course, always when you're in such a situation, we have some kind of congestion, should avoid this in general and think about restructuring your system, distributing the computation. But yeah, it's absolutely right. This is a valid approach, which is also discussed.
Okay, thank you very much. I hope that answered the question. I would now like to welcome our next set of speakers. They're joining us from eProsima. We have Dr. Francesca Finocchiaro, as well as Pablo Garrido Sanchez. They will be presenting their topic, as well as we have Jose Antonio Moral, who will be joining us for the panel discussion towards the ending. To quickly introduce our speakers, Dr. Finocchiaro has completed her PhD in theoretical physics in Madrid in 2018, and then switched over to robotics, where she worked for 1 year as project manager and team lead in eProsima. She currently coordinates the teams behind Micro Ros, as well as the middleware Micro XRCE DDS. And we have Pablo, who is an embedded system developer with eProsima. He is also a PhD candidate at Universidad de Granada. He has a wide array of experience in telecommunications, electronics, software development, hardware prototyping, and so on. So he should be able to answer any of your questions. Thank you very much for joining us, and the microphone is now yours.
Okay, I hope you're seeing my screen, and I guess so. So I'm Francesca Finocchiaro, I'm from eProsima, and I'm going to talk to you about Micro ROS, as the moderator was mentioning, so to the ROS industrial community. So let's get started with a brief overview. So Micro ROS was born as the result of a joint effort between several European companies, namely eProsima, the Firmware Foundation, Bosch, and PIAP. It has been funded so far by the European Union within the framework of the Horizon 2020 research and development project. However, as it is an open source project, it is now benefiting more and more from contributions from a growing community of users. What does really Micro ROS? The aim of Micro ROS is to bring a ROS2 node into a microcontroller. And so why is this important? So nowadays, robots and IoT technologies are each day less of a central unit taking care of all functions and more of an interconnected network of robotic parts, with a topology that is most often characterized by a central part taking care of the most computationally demanding tasks, plus a collection of minor components, mainly sensors and actuators, which are operated by distributed networks of MCUs, which are in charge of highly specialized physical or mechanical operations. And that's where Micro ROS enters the scene by allowing to create a ROS2 node into the MCU. This node, thanks to this, is basically very close to the hardware level and has the possibility to interact directly with the drivers that control the hardware peripherals, which allows a very fine-grained integration within the ROS network and avoids raw data to be sent directly to the central processing unit, which in turn frees its resources for other tasks. And all this is made possible by the very special characteristics with which Micro ROS comes. So let's take a look at them. First of all, it has been designed so to have an architecture which is layer by layer compatible with that of ROS2, which ensures modularity and also interoperability with the ROS2 ecosystem. Also, it allows, well, as I was saying before, to create basically an embedded node provided with basically most of the key functionalities of a standard ROS2 node. It follows client-server logics, of which I will be speaking more in detail later on. It can use several different transport protocols, allowing it to fit a diverse range of use cases. It runs on different platforms, and for this to be possible, it offers a very versatile build system that encompasses the growing pool of the supported platforms. It can benefit of the full range of quality of services that is offered by ROS2. And also, we are constantly working to be up to date with the latest version of ROS2. At the moment, indeed, we support Foxy, and we are also preparing a rolling release for 2021. Finally, we can count on a growing community of users which are actively participating to the development, the port of new platforms, and crucially to our monthly embedded working group meetings. So in this slide, as a first thing, we want to present the Micro Ros architecture, and we do so by comparing it to that of ROS2, which is possibly something which is familiar to most of the audience. So first of all, Micro Ros relies on a client-server logics, as it is composed by two separated libraries, the client and the agent. So the client is the one which is shown here on the right, and basically is the entity that runs on the embedded device, while the agent, which is shown in the middle, is an entity that basically has the task of bridging the clients with the ROS2 world, which is shown here on the left. So very briefly, let's see which are the most relevant aspects in this comparison. So the application components in Micro Ros run directly on top of the RCL, whose functionalities in Micro Ros are complemented by the RCLC, which was mentioning my colleague Ralph from Bosch. This is an additional package which is written in C, and it is offering features similar to those of the RCL-CPP, but tailored especially for fitting into embedded devices. As in ROS2, the RCL lies on top of the RMW, which in this case uses as the underneath middleware the implementation of a wire protocol, which is specifically tailored for resource-constrained environments, which is called the Micro XRC DDS. In turn, this middleware implementation runs on top of a real-time operating system. That is basically an operating system designed to address the needs of time-critical applications and low resources devices. So let's see this layer by layer. First of all, here we are taking a deeper look at the middleware, which is Micro XRC DDS. So this library implements a wire protocol that is designed to bring DDS to resource-constrained devices. It also relies on a client-server architecture, which is then inherited by Micro Ros, in which the clients are lightweight libraries that run into lower resource devices, while the agents are heavier libraries that run on more powerful microprocessors. And they bridge the clients with the DDS world. And in this world, the role of the agent is that of creating a proxy that acts on behalf of the client and interacts with DDS by means of all the standard DDS entities, such as participant, publishers, data writers, and so on. And these entities are created on the agent under a specific requirement of the client. And the agent crucially keeps them in its memory at all time, in such a way that even if the client gets disconnected or enters, for instance, a deep sleep mode, its state within the agent stays alive at all time. So the transport protocols supported by default by this XRC DDS library are UDP, TCP, and serial. And there is also the possibility for the user to define its own custom transport. So here we're speaking of the transports that are able to intercommunicate the agent with the client, okay? Then you also have the other part of the communication, which is the one between the agent and the DDS world. Okay, so we now have the RMW, which is, as I was saying, implemented by the Micro XRC DDS API. And this RMW is specifically designed to meet the resource finiteness of the class of mid-range embedded devices, which are targeted by Micro Ros. Indeed, it can be configured by the user by tuning several parameters at compile time, allowing to avoid any memory usage that is not strictly necessary. And this can be done at two levels. First of all, it can be done at the middleware level, which is shown here in the first line. where the configuration happens by means of calls to RNW functions, which are then passed to the underlying layer and allow tuning parameters such as, for instance, the transport protocol, the IP address, the port of the agent, the entity's creation node, and the IP version. Instead, at the ROS level, Micro ROS uses static memory pools to handle several key parameters whose size can be heavily modified or that can even be disabled. For instance, as I'm showing here in the second line, this happens for the number of publishers, the length of the topic name, the history size, and so on. Once again, thanks to this, the size of the Micro ROS library can be tailored to meet the user's application requirement. So, okay, to conclude this architecture part, I want to briefly comment on the differences between the client support libraries in ROS2 and Micro ROS. So while in ROS2, an application component is always interfaced with either the RCL CPP or the RCL PI, and never with the RCL, in Micro ROS things are a little bit different, as I was mentioning before. Indeed, while the C++ API in principle can be used, as a matter of fact, C++ is not fully supported in every embedded platform. And therefore, we decided that a Micro ROS application is directly interfaced with the RCL. And to implement the functionalities of ROS2's upper layers, Micro ROS uses this RCLC, which is written in C and is some sort of a spin-off of the now not used RCLC library, which was in principle one of the packages of ROS2, and which we now as an organization maintain. And this library provides convenience functions for creating nodes, publishers, subscribers, and also, which was mentioned by Ralph, a deterministic version of the executor provided with LED semantics, dynamic memory allocation at startup, and domain-specific scheduling. So these features are analog to those offered by the RCPP, but are designed to fit into microcontrollers and address real-time needs. On the other end, the RCL, along with the RC utils and the type supports, are plain forks of those of ROS2 with some additions from our side. Okay, so now let's see what are the platforms that Micro ROS currently support, both on the hardware and on the software side. So the client is apt to run on top of real-time operating systems, that is, systems provided with advanced algorithms for task scheduling plus matter abstractions. And they are ideal to run on resource-constrained microcontrollers and to deploy time-critical applications. The RTOSs that we support to date are NATEX, Zephyr, and FreeRTOS, of which these last two are very popular at the moment, and we have been adding them to the project during the last year of development. So these three RTOSs all display, to some degree, a POSIX-compliant API, which is crucial, and also slightly different features and scheduling algorithms. The client also runs on Linux and Windows, which is relevant for simulating and testing purposes. And these are also the platforms on top of which runs the agent, which doesn't run on top of RTOSs. Okay, that said, let's pass to the supported hardware. So the Micro ROS project targets mid-range microcontrollers. At the moment, architecture-wise, we support the ARM, M4, and M7 MCUs on the one hand, and on the other hand, Extensa MCUs. So among these families of boards, the one that we provide official support for are the ones that are shown here on the left. And the typical figures of these boards are a flash memory of around 1 megabyte, a RAM memory of around 200 of kilobytes, less than 500 milliampere of consumption, and they are also provided with the general purpose input-output pins and an extensive set of communication peripherals, such as USB, Ethernet serial, I2C, and so on, which is making these devices ready for a low-level integration with sensors and actuators. Okay, so in addition to these boards that we support officially, the hardware collection that is already part of the Micro ROS family is actually bigger and is growing every day thanks to the contribution of the community. So this slide shows to which other boards Micro ROS has been ported so far, but that's not all. Indeed, we are already working on new parts, and also As a cherry on the cake, we want to mention that Sapphire, which is one of our supported RTOSs, officially supports a lot of boards, more than 260 at the moment, and this number is constantly growing. Supporting basically Micro ROS to those boards that are transport and memory-wise compatible with its resource requirements is super, super easy. Indeed, several of the recent ports that we have been received from part of the community and that we shown on the previous slide have been done to boards that are supported by the Sapphire project. So to provide users with some reference regarding memory constraints, we have recently performed a thorough analysis of the memory footprint of the Micro ROS library as a function of some key configuration parameters and Micro ROS applications. And this you can find on our Micro ROS webpage. And we will updating it when we are going to update our library with some significant improvements that we are planning to do for as concerns the memory consumption. Okay, so let's now take an overlook to the recent developments, features and integrations with which we have been basically busy lately here at Micro ROS. So the first big change which we have been implementing regards the build system. Indeed, during the first almost 3 years of its life, this tool of Micro ROS, the build system, has been basically a collection of cross-compilation packages for building the library for all the platforms supported by the project, which we have been, of course, updating as the project was maturating. And as a fact, to date, it encompasses all the RTOSs and boards that we support. But the big news now is that at the same time as maintaining this tool, lately we gave this approach a twist by compiling a standalone Micro ROS modules that generate libraries for external build systems. The new approach allows to seamlessly integrate Micro ROS into external development environments and establishes an alternative way for users to run Micro ROS into their embedded devices within their own or their preferred development framework. And thanks to this new building tool, we have already been able to integrate Micro ROS into 3 external build systems. First of all, the ESP IDF, which is an environment for programming applications on top of Rtos, which we have proven to be successful on the ESP32 microchip already. Also, we have developed a package that integrates Micro ROS as a module into the Sapphire build system. And finally, very recently, we have been able to give support to the Arduino IDE, thanks to which we could port Micro ROS to the family of Teensy boards and to the Robotic OpenCR. So basically, to sum up, thanks to this twofold approach for compiling the Micro ROS library, those users that wish to use Micro ROS on any of these platforms are basically free to choose either of the 2 ways for compiling Micro ROS that we offer. Okay, so I'm now going to present 3 very interesting demos on which we have been working lately. So the first focuses on the integration of Micro ROS with Move-It2. Move-It2 is a robotic manipulation framework from Picnic able to plan movements according to sophisticated kinematic algorithms. And to demonstrate how flawlessly Micro ROS interacts with Move-It, we have mounted a demo where we display in RVs how Move-It's Panda virtual robotic arm can be moved according to the change in orientation in real space of a board running Micro ROS. So the board that we use for this purpose is a STM32L4 development IoT kit, which is running Sapphire, and we use 2 functionalities that it offers. First of all, it has an inertial measurement unit composed of an accelerometer and a gyroscope with a magnetometer. And the fusion of the measurements fetched by the sensors outputs the pose or quaternion attitude, which provides information on the board's orientation in space. Also, we make use of a user button that triggers the Move-It2 planification algorithms and causes the virtual arm to move to where the board is located. So the pose and trigger topics collected by the Micro ROS app are forwarded to the ROS world, and in this world they are consumed both by the RVs application and by Move-It2. In this GIF, here in the bottom right, we see the RVs interface displaying the whole demo. The board is represented as a red arrow moving according to its real-time position, shown in the top left pane of the GIF. So the robotic arm can be seen to calculate the movement when the user button is pressed in the form of a ghost-like image, and finally performing the movement to reach out to the arrow representing the board. This is one demo. In the second demo that we want to show, we have basically two ROS2 data spaces hosted by two separate subnets, and we want to show how they can communicate over the internet thanks to Proxima's integration service, a tool to intercommunicate protocols with DDS. So in the first data space, we have a ROS2 node publishing a TOIS type message, while on the receiving side, we have two subscriptors in the form of a standard ROS2 node and a Micro Ros node. So in each LAN, what we do is we launch an integration service instance that acts as a WAN gateway over the TCP transport layer, which is offered by FastDDS. This allows the two ROS2 data spaces to be put into communication, notwithstanding their logical separation. And then the demo is integrated with Micro Ros, allowing this remote communication to be brought to the embedded level. So in the video here in the GIF, we can see a remote call between two of our engineers, each in charge of a ROS2 LAN. The first engineer is shown on the bottom right and is publishing a twist topic with a gamepad through the WAN. And the second one, shown on the left, is receiving it. So in the top, we can see him turning on a Kabuki robot operated by an SP32 board with 3 Rtos and a Micro Ros node running on it. This node is communicated with the ROS2 data space via the agent, which allows it to subscribe to the twist topic and to move the robot accordingly. Also, at the same time, is basically executing a turtle scene node, which also subscribes to the same topic and displaces the turtle in the visual interface. So as a consequence, we can see how both the robot and the turtle sim are moving, operated by a gamepad controlled by a remote ROS2 node. Finally, in this third demo, Micro Ros showcases its capabilities in an environment that mimics a realistic industrial scenario like that of a smart warehouse, with a dynamic and distributed system of heterogeneous IoT devices. So the demo was designed, orchestrated, and recorded by PIAP, which is one of the partners of the OFRA consortium, which is the project behind Micro Ros. It presents a mobile platform interacting with a set of sensors and actuators based on microcontrollers running Micro Ros, a Micro Ros client, over 6LoWPAN, and scattered in a simulated warehouse area, both indoor and outdoor. So the mobile base is a scout robot designed for quick recognition of its surroundings, thanks to a localization system providing coherent information on its position and orientation. And it features an onboard computer running a ROS2 node. And provided with an autonomy module in charge of driving the robot all the way down to the accomplishment of a given mission, which is basically to move through the warehouse and then exit. So during the trajectory, the robot steps into a series of environmental devices with which it intercommunicates when they are within the range of the 6LoWPAN. Namely, a humidity and temperature sensor from which it fetches the measurements and sends them to the ground station operator. A door, which can be opened remotely, which is shown here on the GIF. A time-of-flight sensor measuring distances and communicating whether the path is clear or not clear, and a light that can be turned on and off. So the communication, once again, of course, is communicated by an agent running on the onboard computer, which connects to the various Micro Ros clients operating the sensors and actuators as the robot moves across the warehouse. And in all the 5 devices, Micro Ros is running on an Olimex STM32E407 board and on top of Natex. Okay, so another big news is that we are moving forward with the task of bringing the complete ROS2 features list into Micro Ros. So our most recent achievement is the inclusion of a dedicated graph manager into the Micro Ros agent. What we have done is including a DDS participant that scans the network in search of all the available ROS2 entities, such as nodes, publishers, services, and so on, and publishes them onto a dedicated topic, which is then listened to by our RMW implementation to collect the ROS2 graph information and pass it to the user. Also, thanks to this new implementation, Micro ROS is now also able to inject information about its own ROS2 entities into the ROS2 global data space, so that users executing graph-related tasks can get information about which Micro ROS entities are present at the moment. Of course, since we are always concerned about memory, this new graph feature is fully customizable and can be totally disabled in configuration times, as it, of course, consumes resources. Another feature that we are currently working on is that of enabling peer-to-peer communication. This development is at the moment heavily work in progress, but we have already a nice prototype ready to work over UDP via Wi-Fi, which we probed with the SP32 boards on FreeRTOS. The basic mechanism underlying its functionality envisions clients sending information about themselves via broadcast, with other clients listening and being able to connect with them, and starting interchanging information by publishing and subscribing to topics or communicating via services and actions in the standard ROS2 way. At the moment, several features are missing, such as quality of services, but it will be giving it refactorization during next weeks to deliver a more complete functionality. Okay, the very final thing that I want to mention is an ongoing project that is also work in progress, and we're super excited about it. So we're working on the integration of Micro ROS with an artificial intelligence of things project, which is involving the embedded depth AI BW1092 board by Luxonis. So this small device allows to interact with Luxonis depth AI system or module from a microcontroller, which in this case is the ESP32. The depth AI is an open source platform that combines neural inference, computer vision, and machine learning on a variety of hardware platforms. And in the case of the specific board we use for our project, it brings these capabilities to the embedded world. The board features the 3 cameras, making it possible to obtain the metadata coming out of a neural network in the development environment of a small ESP32 MCU. And thanks to the integration with Micro ROS on top of FreeRTOS, it will be possible to bring this data to the ROS2 ecosystem. And this is basically all regarding this project. I now want to leave the word to my colleague Pablo, as we are running out of time. Thank you very much.
Hello everyone, I'm Pablo from Eprosima Micro ROS team, and today I'm going to show you a couple of hands-on demos to illustrate the Micro ROS usage in a practical way. First of all, we are going to see a basic sensors demo that uses the ST Discovery IoT board to implement a Micro ROS node that runs on top of the Zephyr RTOS. In all the demos that I'm going to show, are available in this link in the bottom side of the slides. Using the Zephyr RTOS and plus a Micro ROS node, in this demo we are going to publish data from a couple of sensors and subscribe to a Boolean in order to turn on and off an LED that are on the board. This Micro ROS node is going to be communicating with a serial transport with the Micro ROS agent in order to represent himself into the ROS2 world. Using common ROS2 tools, we will be able to interface with this information. First of all, we have to know that the easiest way for a ROS2 developer to use Micro ROS is using the Micro ROS build system. The Micro ROS build system is a tool in the form of a ROS2 package that allows you to create Micro ROS images that can be flashed in the supported platforms. For this demo, I have prepared a couple of Docker files because the procedure of building a Micro ROS image with the Micro ROS build system usually takes a while. First of all, we are going to see the Docker file in order to see what is happening and what already has been done in this demo. Here, we can see how we are running the Micro ROS build system in form of the Micro ROS setup package to create a firmware. And in this command, we are telling the build system that we are going to use the Zephyr RTOS and this hardware platform, which is the ST Discovery IoT board, which features an MCU with an ARM M4 MCU. Then we tell the Micro ROS build system that we would like to build an application called Sensor Publisher. And that's and we are going to use the first serial transport in the board because this board has a couple of ports. Finally, we just build the firmware, and we have the already a Micro Ros image ready to be used. So let me open this container that you have available here if you want to test it. We open the container, so we have here ready to use the Micro Ros setup tool. If we run the create firmware command, which is the first command that the Docker has already done, we can see that the tool tells us which RTOS are available and which platforms are available also. If we run the configure firmware command, we can see which apps does this Docker include, but of course you can add your own application, your own Micro Ros application, by just dragging them into a folder. Finally, the Docker has already done the build step, so we have here the firmware folder. So now I'm going to show you this board that I have here, and we are going to run the last step in this procedure, which is ROS to run Micro Ros setup flash firmware. And now we are flashing the firmware, the Micro Ros firmware in the board. Meanwhile, we are going to open a Micro Ros agent in order to let this Micro Ros node represent himself in the ROS-I world. I'm going to open another terminal here, and now I would like to tell you a couple of things before running this. That we have the Micro Ros agent available in a couple of ways. You can use it as a Docker image. You can install it by using snap packaging, and also you can install it as a common ROS-I package using the Micro Ros build system. So now I'm going to run the Micro Ros agent and reset the board. And now here we can see how the XCDDS communication happens between the client and the agent. This XCDDS communication, remember, is the middleware that is used in Micro Ros. So now we are going to open here a ROS-I instance, and let use the common ROS tools to see which topics are being published. Here we can see that now we have sensor inertial unit measurement and sensor LED and the sensor TOF. The sensor TOF is being publishing a measurement done by one of the sensors available here in the board, that is measuring distance. First, I would like to show you some of the code in order to see how easy it is to write a Micro Ros application. Here we can see the RCLC code of this application. You have an API that is similar to the RCLCPP, which ROS-I users are used to. We are creating a publisher on the sensor TOF. We are creating another publisher on the MUI. We are creating a subscriber on the LED. Then we are creating an RCLC executor and adding these subscriptions plus a timer. This timer is going to run a callback that is here, that is going to publish the data from the sensors. Okay, and finally, here in the while loop of the application, we just spin the executor of the Micro Ros application. So now that we have a slightly our view of the code, we can see what is happening here. Sensors, TOF. And if I open the webcam here, we can see how if I move my hand on top of the TOF sensor, we can see that the Micro Ros node is publishing the distance between the board and my hand in meters in a ROS-I topic. We also can subscribe to another topic being published by the board, which is the inertial unit measurements. This topic is sending the accelerometer data. So we can see here in the Z axis, the accelerometer of the gravity. If I move the board, we can see how it's changed through all the axes. So this is the second demo of the node publishing. And finally, I would like to show how a Micro ROS node can subscribe to a topic. For example, in this case, I'm going to publish a Boolean that will make this LID here to be turned on. So the LED is turned on. And of course, if we send the 0, we are going to have the LED turned off. And this is a basic demonstration of how a Micro ROS node can be implemented inside of a microcontroller and interface with the ROS2 usual tools. Of course, you also have available services and clients, and also actions, and all the ROS2 entities that are available on the common APIs are also available in the ROS2 ones. You have all the information and all the detailed information about these demos in our web page. And of course, if you want to have more information or ask about some port or something related to Micro ROS, we are also very active on the GitHub pages and repos. So thank you very much.
Okay, thank you very much for that very interesting presentation. I would say that was basically a crash course on. That was basically a crash course on Micro ROS. The presentation was, I think, airtight. Anytime I looked at a slide or any part of the presentation, I had a question, it was pretty much answered within the next slide or the next minute. So thank you very much for that. I do have one quick question I would like to ask. So you have the RCL ROS client library for C already built. Do you also have support for Arduino programming as well? I think you mentioned that it is either being built or ready shortly.
Yes, we have, as Francesca told, we have some boards and some Rtos supported using the Micro ROS setup, which is the official build system, but we also have some other kind of tools that let the user build an Arduino image with other tool chains. Arduino IDE is one of these external build system, and we provide an already built Micro ROS library for some boards that are used in the Arduino IDE.
Okay, thank you. Yeah, I think chat is also very happy with the presentation and a lot of accolades flowing in. I think we can take one question now. There was a question to Francesca, which is, has Micro ROS been used with VxWorks, and are there specific requirements to the compilers using, for example, C99 support or C++11? I think this was also already addressed in the slides for C99. Could you comment on this?
Can you repeat can you repeat the whole question?
Yeah. Has Micro ROS been used with VxWorks? Are there specific requirements to the compilers, such as C99 support or C++11?
Okay, so maybe Pablo can help us here because they have been working on this integration with VxWorks.
Yeah, as far as we know, VxWorks, in VxWorks, we can run the whole ROS2 with its DDS middleware, because we have here a college in Proxima that runs ROS2 and fast DDS on VxWorks. But in fact, one of the projects that we have been doing last month is porting the Micro ROS agent to VxWorks. But if you want to know about the Micro ROS client, of course, it can be run on VxWorks. We don't have the port done, but Micro ROS client only needs C99 support, a standard library, and some function of the POSIX API to be compatible with some function of the POSIX API. So I guess that VxWorks will fit with these requirements, and it should be completely possible to run the Micro ROS agent in VxWorks.
Yeah, let me add that we mainly use the client support library RCL as is this layer, and just deactivate some functionality that is not available on microcontrollers, such as file systems, etc. And that RCL is built very, let's say, with compatibility in mind, as strict POSIX and C99 standards. So that can be ported to many Rtos as quite straightforward.
Okay, thank you. Ralph, I think you also saw there was a follow-up question and then you responded to it on Swapcard as well, but just for the stream,
Yep.
I would like to repeat the questions and then you could also maybe discuss the answer.
Yeah.
So to repeat the question, we had the first part, which was, in your opinion, is one of the major contributors to the complexity in Executor design, the desire to maintain DDS QoS.
Yeah.
And the follow-up question was, how do non-ROS2 applications using DDS deal with scheduling? Do they hand everything over to the middleware? Do they not run on the same problem with loss of application knowledge?
Yeah. Yeah. So after sending my answer, I saw that it were actually two questions. So the first one I answered already, that yes, the QoS mechanisms are driving the complexity, at least if you want to consider them. If you, let's say, walk in the way, then yeah. What if you do not have ROS, if you directly work against the DDS API? It's to understand that DDS does not provide, let's say, a execution management model like ROS does with the executor. So you will have to implement something application specific. You will have to decide how to distribute your functions, computables, however you call it, to tasks, processes, what is available from your operating system, and when to trigger computations. And of course, DDS can help you in the sense that you can, on the one hand, you have the possibility to register listeners to certain events, or you can do this explicit wait and be notified once information is available, a message arrived. But that's then up to the application developer to develop this scheme. And ROS with the executor, let's say, gives a framework for that. But of course, you can also work around. You saw in Pablo's presentation in the code, for example, he instantiated an executor, but then actually did two things. On the one hand, he interacted directly with the hardware in outside of the execution management mechanism of ROS, and then called the spin once for 100 milliseconds, and then did another iteration. Even that is possible, yeah.
Okay, thank you. Yeah, we have one more question. And to be honest, when I'm somewhat new to Micro ROS as well. So when I first started reading up on this, and I sort of had this question in my mind as well. So what is the differences between ROS serial and Micro ROS?
Who wants to take it?
I can say something if you want.
Yeah.
As far as I know, Micro ROS is an evolution of ROS serial for ROS2. ROS serial is intended for ROS-I, and it's just a protocol to communicate a microcontroller with the whole ROS system. When we talk about Micro ROS, we talk about having all the ROS2 layers being ported to the microcontroller. So you have all the concepts beyond the communication, beyond the middleware. You have all the concepts available to develop microcontroller applications. Also, regarding the middleware, we have to say that Micro ROS uses a middleware called XRCDDS, which is a standard by the OMG. This is a standardization and standardized protocol that allows a lightweight client to represent himself in the DDS world. So we are using a more advanced middleware, and of course, we are offering an extended API more similar to the ROS2 one. Maybe Ralph wants to add something.
Yeah, I want to add two things. So the one is, by having the API on the microcontroller, it's much easier to, let's say, port pre-developed code from standard Linux and ROS to Micro ROS. That was especially an interest by Bosch in this project, that we do use ROS in pre-development, and this, let's say, lowers the gap in bringing this on tiny microcontrollers for consumer robotics devices. And the second big difference is in ROS serial, the software on the microcontroller appears as one ROS node with limited functionalities, whereas here you can now have multiple nodes on the microcontroller, and they will appear as multiple nodes in the whole ROS graph. You have all the tools available, parameters, services, topics, and can access them all with the standard tools. So that's, let's say, feature complete, and as you know from ROS2.
Yeah, so I also learned this as Francesca was presenting, and I started to understand, okay, what really is Micro ROS. When I used ROS serial, it was just one node on a microcontroller, but now you can really have a complete environment on it, although it is still a microcontroller. Yeah. I think we don't have any more questions per se. But we can take a look at the poll questions we had posted. The results might be interesting for you. The first question we'd asked was, are you interested in using Micro ROS in the future in any of the following domains? So we had mobile robots with a response of 24%, drones with a response of 10%, manipulation was 34%, raw sensors for data acquisition or sensor fusion was 21%, and 10% were interested, but they did not have a very specific use case yet. So in all, we had 17 votes for this poll. The next question we asked was, what's your favorite RTOS for microcontrollers? We had 12 responses. 50% of them responded with Flea RTOS, which seems to be quite famous now. Only 8% used Zephyr, and 33% used bare metal with Arduino IDE, and 8% had used some other RTOS. So was the response to this specific question, RTOS, was this somewhat expected?
At least it confirms our decision to discontinue the support for NUDX. So originally the project had started with NUDX, also for links to the drone code community. And later we decided to include FreeRTOS and Zephyr as well. And that was obviously the right decision.
Yeah, so the last question we had was, how do you integrate microcontrollers in your robotic systems? 42% responded ROS serial, which probably means it's still ROS-I. 11% responded Micro ROS, 21% responded custom protocol, and 26% responded not using microcontrollers at all. So do you think 11% for Micro ROS is good enough number now, and do you expect it to increase going forward, especially once ROS-II takes a proper route into the robotic society?
I think that's what we expect, yeah, Pablo.
Yeah, I think so. We have been developing Micro ROS for 3 years, and I think, in my opinion, until before this summer, until the Foxy release, we don't have a stable system. And now we are working really hard to provide a production-ready system. But of course, the Micro ROS system is under development, and we have already a lot of work to do before people can adopt it in their production robots.
Francesca, do you have anything to add to this conversation?
Well, yeah, as you were mentioning, I mean, that it all depends a lot also on whether the companion robotic system used in the heavier or, well, more powerful microprocessor is either ROS-I or ROS-II. So because we have had a lot of people contacting us, telling us they were thinking about migrating some use case or project that they have to ROS-II, and of course, some project that they had on ROS-I and ROS-I serial to ROS-II with Micro ROS. So it also depends a lot on that. And since Micro ROS is relatively new, and as Pablo was mentioning, it has been stable only for the 6 last months. It's normal that the adoption is being somehow slow. And we hope that it now will have some sort of a fast forwarding situation, because, you know, the adoption it's a sort of a process that, but I think that it all depends a lot on that.
Yeah.
But let me add 2 things. We have also very active Slack channel. So if you want to reach out to us with your project, you have problems, use it. And we meet regularly in the embedded working group. The schedule is published on index.ros2.org, so where all working groups are listed, or in the normal calendar. Also, if you have interesting projects that you did with Micro ROS, or you want to learn more, just join these events where we report on the developments, where we interact with the community, and where also companies like these recent works that Francesca showed present their works with Micro ROS.
Yeah, and in general, I mean, the best option is to go to the embedded working groups to present any issue that you might have with microcontrollers, or doubts, technical problems. But apart from that, we are also very responsive if contacted, I mean, privately. So we also, how do you say that? So we invite you to do so, okay, to contact us and show us your project or use case, and we will be happy to see whether Micro ROS can help with that or anything.
Okay, thank you everyone for presenting. Thank you very much for this very interesting conversation that we had. I hope you continue to enjoy the rest of the Inertial conference. And thank you all the viewers as well, and for the interesting questions and for the poll results. Thank you everyone. Bye.
Thank you.
Thank you.
Thank you. Bye.